Hi, in this video we present a very important technique of calculus of primitives, which is the change of variable formula. To present this formula, let's start with an example. Consider this primitive, the primitive of e to root of x. And we may think that if we introduce a new variable, y, defined as the root of x, this would simplify the function e to root of x into the function e to y. So we may wonder if computing the primitive of e to root of x in the variable x is the same of computing the primitive of e to y in the variable y. If this would be true, the calculation would be easy because the primitive of e to y is just e to y. And therefore, restoring x, it would mean that a primitive for e to root of x is just e to root of x. However, this is entirely false because, as you can check, differentiating e to root of x, you don't get e to root of x at all. And in fact, the problem is that something here is missing, and now we will try to understand what is missing here. To understand this point, let's take now the question from a general point of view. So let f of x be a generic function of x, call capital F of x a primitive of little f, which is the goal of our calculation. Suppose that we think that introducing a new variable y, which is defined through a certain function of x, the calculation gets easier. Now, when we say y equal phi of x is a change of variable, we mean that to each x it corresponds a y, but also the vice versa. To each y it should correspond an x. So formally, this means that this correspondence, x to y, is a bijection. So it's invertible, and in fact, this function is nothing but the inverse of this one. Okay, so now the remark is the following. If we take a primitive of little f, and we evaluate on the x that corresponds to y through this change variable, so to psi of y, and we differentiate this quantity, we get the following. By the chain rule, the derivative of this is the derivative of capital F, evaluated at psi of y, times the derivative of the argument psi prime of y. But since capital F is supposed to be a primitive for little f, here we have little f at psi of y times psi prime of y. Now, this relation says that the derivative of this function, with respect to y, is equal to this function here. So, in particular, this is one of the primitives of this function. In symbols, this means that f at psi of y is equal to a primitive for f little f psi y, psi prime y in the variable y. But since this capital F was supposed to be a primitive of little f, this relation can be seen also in this way. You take the primitive of the function little f, that is a function of x, and we stick in place of x this expression psi of y, and you get this. So we have this identity. Or in other words, a primitive of f in the variable x now is the right-hand side, which depends on y, when we replace by y what corresponds to x, so y equal phi of x. And that's the change of variable formula that we see here. Now, the scope of any rule of calculus for primitives is just to simplify the calculation. So we do something to get something better, easier to be computed. And the idea should be also here that the right-hand side should be easier than the left-hand side. Apparently, this is completely false because the right-hand side contains a lot of stuff here. There is the inverse of this change of variable, so the function that gives the old variable function of the new here, etc. But think about this part here is just the function f written in the new variable. So this is what should be easier because we introduced the change of variable just to simplify the function f. And now the second point is this coefficient. This coefficient is the important part of the change of variable formula because it was just what was missing in the initial idea. So let's see how it works in an example. So let's go back to the primitive of e to root of x and introduce the change of variable y equal root of x. So this is the set y function of x, so new variable function of old, so that's the function phi. We need the inverse function of this, so we need to explicit x function of y, and this can be done easily. X is equal to y squared. That's exactly a one-to-one correspondence because x must be positive, and when x and y are positive, the square is invertible, and this is a bijection. So this is the function psi of y. We need the derivative of this function, which is easily 2y. So we have now all the ingredients to apply the formula. This becomes c to y, and then, so this is this part here, and then we have the factor psi prime y, which is just 2y, and that's the new primitive we have to compute, which is a bit easier than the initial one. At least here we may imagine that with an application of a calculus by part, we will solve the problem. In fact, we may think that e to y is the derivative of itself. Therefore, this is 2y e to y minus, now derivative moves from the exponential to 2y. Derivative of 2y is 2, so we get this, minus 2 primitive of e to y, which is now the primitive of an elementary function, so we get, finally, this result, 2 e to y times y minus 1. Now, this says that the calculation of the primitive is over, and therefore, if we want to restore the variable x, we have just to plug here, in place of y, not the letter x, but what corresponds to x, to y in terms of x, which is just the root of x. So we get this formula. Well, that's it about the application of the change of variable on this example. Before we illustrate more examples, let's do just a remark on the general formula. Now, the important fact is that when you look at this formula, this is normally the starting point, so your primitive, and this is what you want to compute really, because this is what you get after the change of variable. Now, as we said, this part here is nothing but f as seen as a function of y. This does not mean that you change letter x into letter y. It means that you have to replace, wherever you see x, you have to replace the expression psi of y, or if you see the expression phi of x, you just write y in place of the box phi of x. An interesting remark consists in the transformation of this factor, informal factor dx, into this one. Because since x is just this function psi of y, the idea is that if you differentiate both sides of this identity, the derivative of x would be the derivative of psi of y, so psi prime of y times the derivative of y. So that's more or less the idea to memorize quickly this trick. Okay, so let's see now a concrete example like this one, where we can illustrate some other features of the change of variable. The first feature is that in general there is not a standard change of variable. This is a little bit creative operation, so where you have to find out which change of variable really simplifies the problem. So for example, here we could be a lot conservative, saying that let's introduce new variable y just 2x, for example. This means that x is y over 2, and dx is just the derivative of y over 2 is 1/2, dx equal 1/2 dy. Now, if we do this change of variable, our primitive will become, since there is only y equal to x, so this becomes root of e to y minus 1. So the function in the variable y is this one. Dx becomes 1/2 dy. So the new primitive is this one, which sounds to be a little bit easier, but not particularly easier. A more aggressive change of variable could be this one. So why don't we set the interior exponential here equal to y? So this means that 2x is the log of y, or x is 1/2 log of y. So you can see that this change of variable can be really inverted, so it is a true change of variable. And dx, the derivative of x, is 1/2 derivative of log 1 over y dy. And that's the conversion dx into dy. In this case, our function here becomes root of, this becomes y, so root of y minus 1. That's the function in the new variable. And this is the dx dy, so 1 over 2y dy. A bit better than the other case, because we basically eliminated the exponential, but still we remain with this root. So we may think to be a little bit more aggressive, saying that why don't we take all the argument of the root, which is pretty much as the previous change of variable. In this case, we would get just a little simplification for the root, but not particularly different. An extremely more aggressive change of variable is the following. Why don't we take for new variable y the entire expression here? So why don't we put y equal root of e to 2x minus 1? So in this case, we can invert this relation, y squared equal e to 2x minus 1. So e to 2x is equal to y squared plus 1. Therefore, 2x is log of y squared plus 1. X equal 1/2 log of y squared plus 1. In this case, when we do the change of dx dy, we see that dx becomes 1 over y over y squared plus 1. As you can see, the more complex is the change of variable, the more involved is this factor. But in this case, this is the new primitive to be computed. So as you can see, the function gets easier and easier, but the dx dy get more complex. However, the last primitive to be computed has something particular, because it is the ratio between two polynomials. And that's a standard class for which there is a general argument to compute the primitive. So in this case, we are safe. This is definitely the best choice we can do. We don't need to know that algorithm now to complete the calculation, because we can just write that as y squared over y squared plus 1. We do just a little trick to add and subtract 1 at numerator, and then split the fraction, taking y squared plus 1 divided y squared plus 1. This is 1 minus 1 over y squared plus 1. Now, since the primitive of the difference is the difference of the primitives, we have primitive of 1, which is y, minus primitive of 1 over y squared plus 1, which is the arctangent of y. That's it for the calculation of the primitive. We have to go back now to x. Just remind that y is root of e to 2x minus 1. So this yields the final result for the primitive. The usual way to introduce a change of variable is to set a new variable function of the initial variable, as we have seen in the example so far. But there is another way to do a change of variable, which is doing exactly the opposite. So setting the old variable as function of the new. This is the case of, for example, this primitive of root of 1 minus x squared. Now the point is an algebraic trick here to simplify the root. We want to transform y minus square into a square. And to do this, we profit of a remarkable identity between sine and cosine. You may remind that cosine squared plus sine squared is always equal to 1. So for example, 1 minus sine squared is cos squared. So I can transform 1 minus sine squared into a square. So why don't we put x equals sine of y? As you can see, this is a little bit strange, because I'm not setting a new variable function of the old, but doing the contrary. I'm saying the old variable is function of a new. Of course, since this must be a change of variable, there will be also a y function of x. And this can be easily found here, setting y equal arcsine of x. But normally you may think that if I would say, let's put y equal arcsine of x, probably no one would find this particularly logical step to do. Okay. Another feature of this change of variable is that here we have already the x, old variable, function of the new. So the function you see here is what we call the psi in the notation. So when this is important, because when you have to compute the conversion from the x dy, you just have to differentiate this relation. And you get dx equal cos y dy. So if we do that, we get that this is the primitive of root of y minus sine y square, which is a root of cos square now, so absolute value of cos, times dx dy, so cos y dy. So this yields this primitive absolute value of cos y times cos y dy. We can do a little bit better than this, because since y is the arcsine of x, this quantity belongs to the range minus pi half by half. Therefore, for such y's, the cosine is positive. Therefore, we can just write that cos y in the absolute value as cos y, and this is cos y squared. Now, so after this change of variable, our initial primitive turns out to be this new primitive that could look a little bit easier. In fact, we can compute by parts, writing cos squared as cos times cos. One of the two cos is the derivative of sine. Applying calculus by parts, formula we get sine y cos y minus, derivative moves from this factor to the other. So we have a sine y derivative of cos y, which is minus sine y. So at the end, we have sine y cos y plus new primitive, which is the primitive of sine squared, which is pretty much like this one. But reminding of the fundamental identity of sine and cosine, so sine squared is 1 minus cos squared, we can just write this as sine y cos y plus primitive of 1, which is of course y, minus our initial primitive. Now we can use this as an equation for the primitive of cos squared and deduce that the primitive of cos squared is 1/2 sine y cos y plus y. So this completes the calculation of the primitive, and so we can go back to the initial problem. So the primitive of root of 1 minus x squared is equal to 1/2 sine y cos y plus y, where y is the arc sine of x, and x is the sine of y. So returning back to x, we can say that sine y is x. This y is arc sine x. And what about cos y? We could write cosine of arc sine x, or a little bit better, reminding of the fundamental identity, cos squared plus sine squared equal 1, we can say that cos squared is 1 minus sine squared, so cos is plus minus the root of 1 minus sine squared. And since cos here is positive, remind y is the arc sine, so between minus pi half and pi half, so cosine is positive. This is the positive root. So cos y is root of 1 minus sine squared. And since sine y is x, this is root of 1 minus x squared. And this finishes the calculation of the primitive of root of 1 minus x squared. Well, that's it. Now it's your time. And as usual, the best thing to do is to do practice by computing primitives. The difficult part is, of course, to find the right change of variable that really simplifies the problem. In certain cases, there are standard change of variables, but in general, it is better to try to do experience directly. So try to see what happens with different change of variables, to see which one is better. This is also part of the game. Okay, good luck and see you soon.